Hello everyone, welcome to topic 9.1, Introduction to Entropy. By the end of this, you should be able to identify the sign and relative magnitude of the entropy change associated with a chemical or a physical process. So we were introduced to the idea of entropy in 7.14. Entropy, S, can be described in different ways. Entropy is a measure of the thermal energy of a system divided by a unit of temperature, which is in Kelvin. This energy is unavailable to do useful work. Entropy can also be thought of as a measure of the energy lost to the molecular disorder or randomness in a sample. Entropy has units of joules per Kelvin. Positive values of entropy indicate that the system has increased in entropy, and negative values indicate that the system has decreased in entropy. The third law of thermodynamics states that the entropy of a perfect crystal at 0 Kelvin is 0, and this is because it is perfectly ordered and not moving. So there's no thermal energy, and there is no randomness in this crystal. It is perfectly structured and ordered. Consider two particles in a very tiny container. The image Imagine, I think that's supposed to be imagine. I'm sorry. Imagine that the container has two sections. There's one way to have both particles on the left, and there's one way to have both particles only on the right. There are two ways to have one particle on each side. So it is more probable to have one particle on each side because that's got greater entropy, and that's more favorable energetically, which means that if we have a system with two particles in two sections, it is more likely that at any given time the particles will spread out so that there is one in each section. In an actual chemical system, like a beaker or a balloon, contains a huge number of possible sections. In science, we call these invisible sections, like we see in the image above, microstates. When the particles or the energy in a system are more spread out into the microstates, we say that the system has more disorder or entropy. If the particles or the energy in the system are less spread out amongst the microstates, we say that the system has less entropy or disorder. Consider the common phases of matter: solid, liquid, and gas. The solids have regular arrangement of their particles. The particles are not spread out. They are in a fixed position with only vibrational kinetic energy. So that means that they sit in one spot and they fidget. Solids have the least amount of entropy, and we see that over here, right? They stay in one spot. It is very ordered, repeating pattern, so they have very little entropy. If we look at liquids, particles in the liquid state are able to move within their volume. So they have greater freedom of motion and are able to move throughout the system, and thus are in more microstates within the fixed volume, and are therefore able to have greater entropy than a solid. Gases have the greatest freedom of molecular motions, and they are able to expand to fill the volume of their container. This increases the disorder and means that the matter and energy in the system is dispersed into the greatest number of microstates, because with the liquid, they can only occupy what the states within their volume, but a gas will fill the whole container, unlike a liquid, and so there is a lot more microstates available. This results in the greatest entropy. So gases have a lot more entropy than a liquid or a solid. If you place the same amount of gas into two containers with different volumes at the same temperature, the gas in the container with a larger volume will have greater entropy because there's greater disorder and a greater dispersal of matter in a larger container. There's more available microstates, so there's more disorder that is possible, and the universe and energy tends towards disorder. Okay, that's thermodynamically favorable. When you look at an equation, you can see if there's an increase or decrease in entropy one way by comparing the moles of gas on each side of the equation. If the product side, so you make more moles of gas, then we can say that the entropy of that reaction has increased, and delta S, or the change in entropy, is positive because you have gone to substances that are able to have a greater disorder, like gases. Entropy also increases when energy is more dispersed within a system. We can also compare two systems that are identical aside from temperature. Based on kinetic molecular theory, the system with higher temperature will have particles that have greater average kinetic energy. This energy distributed into the particles will be greater, and this leads to greater entropy as the temperature of the system increases. So here we have a series of, or a summary table depicting when entropy increases and entropy decreases, so becoming more and less disorganized. Okay, and this just summarizes what was up in the notes prior. And then below in these images, we both show, both of these show increases in entropy. And this is kind of hard to see, but that is a forward arrow there. So decomposition reaction, this is a gas because it's not regularly ordered, and these both are gases. So we go from 2 moles of gas to 3 moles of gas total. So there is a net increase in the number of moles of gas. So our disorder of the system increases because we make more gas, and the entropy increases. Dissolving allows this solid to enter into an aqueous state and have more microstates available for it to occupy. So because it goes from being able to occupy very few microstates to quite a few microstates in a solution, this is also an increase in entropy. Okay, so let's look at this next one. So for each of the following pairs, we are going to choose the substance with a higher entropy at a given temperature and then explain our reasoning. So when we look at this, for CO2 gas to CO2 solid, we're going to pick the one with the higher entropy. And from our notes, we know that gases are able to occupy more microstates and thus are able to have more entropy and a greater disorder. So gases have higher entropy because they move freely, expand to fill their container, and can occupy more microstates. And remember, when we say occupy more microstates, we mean a greater disorder. Okay, so looking at helium gas at 2 atmospheres and helium gas at 0.02 atmospheres, when we refer back to our notes, we know that if we have less, it has more space available to it to occupy. So we would say that helium gas at, and I'm going to actually circle it above so I have more room. This one would have higher entropy. It has more freedom to move. And so thus has more microstates available. And results in greater entropy. Okay, so the reaction arrow in our next one isn't there, but that's where it would be. So calcium carbonate makes calcium oxide and carbon dioxide gas. So we're going to look at which side of the reaction would have greater entropy. Well, solids, remember, have very little entropy. They are fairly regularly arranged. They don't have freedom of movement, and so they have low entropy. However, we know gases have high entropy. So this side would have higher entropy. Okay, and it's due to carbon dioxide gas, right? Gases have more freedom. So there's greater disorder. Okay, now I want you to press pause on the video, and I want you to attempt this next one. So the formation of ammonia is an exothermic reaction that is spontaneous or occurs at low temperatures, and it is shown here. For A, you're going to pause after I read it. Complete the reaction showing one of the nitrogen molecules reacting with hydrogen. So it says 1. So please pause the video and show one nitrogen molecule reacting with hydrogen. Okay, and so you should have gotten this, okay, where you see one nitrogen molecule over here splitting and forming 2 ammonia. And so for each nitrogen molecule, I need 3 hydrogens. So that means that for total, I'm going to react with 3 different hydrogens. Okay. So now we're going to answer B. So we did A. Now we're going to answer B. Did the entropy of the system increase, decrease, or stay the same? Justify your answer. Well, they're all gases, so we need to count the total number of gases we have present in the beginning and at the end. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 2, 4, 6, 8. Okay, so we see a decrease in the amount of gas. So this also tells us that the entropy will decrease because we have fewer states of randomness. Okay, so fewer molecules. And the reason being, let's state it again, is that we have 10 moles of gas versus 8 moles of gas, and because we have less gas, it is therefore going to have fewer arrangements overall, and thus have a decrease in entropy. Okay, thank you for tuning in. Please complete the UDs, check your work, and have a great day.